Yeah, so today we will be talking about developing embedded Linux applications with Qt. I like to subtitle this talk typically with the talk that I wish that I had given, or had been given about 4 years ago when I started doing embedded Linux development. Today I'll cover many of the things that you need to know to do any embedded Linux development, and then how you use Qt to make that even easier. So I'll start with a short introduction for those who don't actually know who I am. My name is Andy Nichols, and I am a software engineer at Digia. I've been working with Qt for the last 7 or 8 years. I was actually living in the United States, where I'm from, and was hired by Trolltech, or I was hired by the Qt team back when it was still Trolltech, and then I was working inside of Nokia throughout the entire Nokia years, and then I have since moved to Digia after the fall of the Qt team at Nokia. You may have seen me online. I go under quite a different name. My IRC handle is Nichols, and it is the same handle on Twitter as well, and these are perfect places to reach me from. I guess I should also say some of the things I've been working on. In addition to embedded Linux, I also do the low-level graphics in Qt, working with the Qt platform abstraction. I'm also the maintainer of Qt Wayland, and I also did a lot of work on iOS with the multimedia side, both the iOS and OS X. So today we'll be talking about the following things. This is a short outline of those. Naturally, the first place to start when talking about embedded platforms is the hardware, so I'll quickly go over some of the main hardware you see. Then we'll talk about the software that actually runs those devices, and what a sysroot and a toolchain are. Then I'll talk about the build root tool suite, and then Qt Creator, which is our IDE. And then if we have some time, I'll give you some tips and tricks when dealing with embedded Linux with Qt. So first off, the natural place again is to start with the hardware. And of course, the first thing you think of is the CPU and which CPU to use, which CPU type. Generally, this is either going to be, or almost always these days, it's going to be an ARM. I mean, it's completely ubiquitous. I can guarantee you that almost every one of your phones in your pockets is powered by an ARM processor, with the exception of maybe a few. Then there's also MIPS, and of course x86, Intel x86. There's also PowerPC, but as of late I've noticed a declining trend in that direction, at least. Again, the most popular being ARM, and one of the things to remember with the ARM processors, or one of the things that's commonly, people are commonly mistaken or use these or interchangeably, is the difference between the family name and the architecture of ARM processors. So this just gives a quick summary of what you'll see in the field. First off, on the lower end, and generally this is the lowest ARM processors that Qt 5 will really support. You can go slightly a bit lower, but you have to lower expectations quite a bit. So the ARM 9 and ARM 10 family of processors, they use the ARM v5 architecture. And generally this is going to be processors without hardware floating point support. Many of them don't have GPUs on the system on chips that they come in. And so you're going to have to limit yourself to widgets for the most part there. Then you also have the ARM 11 family, and this uses the ARM v6 architecture. And that's what I'll be showing today. That's actually been popularized as of late because of the popularity of the Raspberry Pi. And then the almost ubiquitous Cortex-A series of, or the family. This is the A8, the A9s. This is the quad cores in your phone. And this is ARM v7 and higher, with maybe the exception of the new Apple devices, which are ARM v8. And as I previously mentioned, these CPUs don't typically exist alone. They typically come in what's called a system on a chip. I guess this is not too terribly important to understand, but this is actually the chip from the Beagle board. I think it's TI OMAP 3530, something very, very close to that. And you can see it has, on the actual die, it has both the CPU, the DSP, and the PowerVR SGX graphics accelerator. Which I guess brings us to my next point. Something very important for Qt 5, especially on embedded, is the GPU. With Qt 5, we actually take full advantage of the GPU, unlike Qt 4, which made it quite difficult to actually use any graphics acceleration you actually had. But here we're actually using OpenGLES2 and offloading as much as possible of the UI code to the graphics coprocessor. And in this space, the most popular of the GPUs is the Imagination Technologies PowerVR GPU. You see this in the Beagle board device, as well as almost all Apple devices, with maybe the exception of a few that are Broadcom video core devices. The Raspberry Pi that we'll be using today is using the video core GPU. And then there's also the Vivanti GPU series that's in the iMac 6, the Google Chromecast. I'm not sure if that's available here yet. But this is an affordable GPU as well. There's also other series of processors, the Mali, available from ARM, and the Tegra from NVIDIA. In addition to the GPU, one of the common things that you'll be seeing that's very important these days is the wireless, and you need to recognize that you need Wi-Fi, Bluetooth, maybe even NFC. But that generally covers the basic hardware that Qt supports. I'm sure there's all other manner of things you could put in there, but Qt has direct support for taking advantage of those things. But so if you've picked your hardware, then you're going to have some software to actually run this hardware. And starting at the very lowest level, you need the bootloader. This is the first piece of software that you need to concern yourself with. This is what actually is responsible for loading the kernel. The most popular bootloader you'll see in the embedded Linux space is referred to as DOS U-boot. And the good thing about this is that most device manufacturers will provide the patches or the configurations needed to use the open source DOS U-boot source code as their bootloader. In other cases, you'll see proprietary, potentially multi-stage bootloaders. In the case of the Raspberry Pi, they have a custom bootloader code just due to the unusual nature of the Raspberry Pi's architecture, where you need to boot the GPU first, as the Raspberry Pi's processor is actually a multimedia, or intended to be a multimedia coprocessor. You need to load this binary blob of the GPU firmware just to get to the point where you can load a second stage bootloader to load the kernel to boot your Linux OS. The next thing, of course, is the kernel. This is responsible for then exposing all of the functionality of your hardware that you have available to your OS. Some of the things to keep in mind with the Linux kernel is that you're able to customize it. And for each given piece of hardware, many manufacturers will provide default configurations for the standard Linux kernel. And they'll either do this in conjunction with other patches that they need to make to the kernel or make available for the kernel. But you'll typically find these in the arch, then the arch that you're using, /configs, and then your processor name, _defconfig. You can also make additional configurations to this defconfig, or just make one completely from scratch using the kconfig tool. And there are GUIs available for this, both in-cursive based if you only have console available using make menu config, and Qt4 based configuration by using make xconfig. Another thing is that once you've built the kernel, you'll see these images that you actually need to put onto the device to get loaded by the bootloader. generally you'll see something like Z-image or U-image. It's usually the difference being compressed and uncompressed. There's a couple of other options, but that will depend on what your bootloader actually supports. And in addition to that, you'll need to make sure that you copy any firmware or proprietary modules to the user file system as well. These will get loaded after the kernel has actually started bringing up the hardware. Which, again, brings us to the next point, the final layer of software being the userland file system itself. This is all of the application libraries and then utilities you need to run on the actual hardware. So that pretty much covers what you need to put on the device itself. But then to get to that point, or to actually build additional software to put on the device, you need what's called a sysroot. A sysroot is a representation of the software that will be part of your image, but also including all of the development files. So that means the include headers, like the contents of user include, whatever proprietary headers you may have, the .so files so that you can actually link against the libraries themselves. And if you're fortunate enough, also the debug symbols, so that when you're debugging on the device, you usually don't have enough space to flash both the libraries and the debug symbols, which can be an order of magnitude larger than the libraries themselves. So you can keep these files in the sysroot, and that exists on your host machine that you'll be building from. That way, when you're debugging, the symbols will get loaded on the desktop only, and you don't have to put them on your device to get a meaningful stack trace. You also need to have a tool chain. And the tool chain consists of the cross compilers and the host tools. These are tools that are intended to be run on your host machine. So in this case, an x86-64 desktop. And they build code that's intended to be deployed and run on the device. So in the case of the Raspberry Pi, I have a compiler that runs on x86, runs on this machine, but generates code that will only run on ARMv6 and higher. As far as host tools goes, the compilers you're typically going to see is GCC, the linker, those things. The host tools would be stuff like QMake and CMake and the make auto tools. So now that you know what you need, here's how you get them. One of the most popular ways to get an image, a sysroot, and a toolchain is to actually use the Yocto project. And the Yocto project consists of a culmination of several different projects that we were using in the embedded Linux community, combined together and somewhat standardized. So some of these tools you may be familiar with: the Open Embedded project, the BitBake build system, the Hockey distribution. And Yocto is also set up or organized into these meta layers. So you can build a distro using individual parts. So maybe you defined a recipe that defines what a base layer system is, like what packages, libraries you need to install into your sysrooted image. And then you can then take additional layers that are maybe provided by device manufacturers like Freescale, or device providers like Freescale and Texas Instruments, that actually are distributed as part of the VSPs that include the drivers, the kernel patches that are specific to their hardware. And then you can then swap out that meta layer based on what hardware you want to actually build for. One of the other options that we're actually pushing, I had a talk yesterday on this, is Qt Enterprise Embedded. In this case, we're actually providing all of the tools for you, or Digia is actually providing all of the tools for you, the device image, the sysroot, and the tool chain. This is something that is, again, available from Digia, and you can contact us if you're interested. But what I will be talking about today is something that is quite easy to explain a lot of these points, and that project is called Buildroot, subtitle Making Embedded Linux Easy, which is something a goal I can truly appreciate. This project is it's basically a build script where you define a recipe of what you want in your image, just an image, and you run make. And it will generate the sysroot, the image. You flash the image to the device, and then you use the toolchain and sysroot that it provides to build software. So I'll show you how that works right now. So let's see. So what I've done is actually pulled down and built a build root system. As you can see that. And what it provides is very similar to the kconfig tool. I can say make xconfig, and it should open up a configuration dialog where I can actually select all the parameters that I want to make to build for a device. Since my target was actually the Raspberry Pi, I've selected ARM Little Endian, and I specified the actual target architecture itself down to the point where it's the exact CPU of this thing. And so it's an ARM 1176JZF-S, which, you know, I looked up, of course. You're able to set other options like where do you get the tool chain from? So in many cases, I think I have a short slide about that actually. In many cases, the tool chain can be provided for you. Like maybe one of these companies are actually offering a pre-built tool chain that guarantees certain quality and optimizations when run on certain hardware types. So one of these options, one of the most popular options was the code sorcery toolchains, or I do believe it's just sorcery now. But their toolchains are widely available, and in the build root script, you're actually able to select these pre-built, pre-released code sorcery releases for your toolchain. There's also the Lenaro provided toolchains. And in cases where maybe you have more specialized needs, or you have some hardware that is maybe a bit uncommon, you're actually able to build your own, or roll your own toolchain quite easily using this tool called CrossToolNG. And that also has a similar kconfig configuration where you can basically set, I want this GCC version, potentially from this location, with these patches, and each little part of the toolchain, and for what architecture, with what optimizations. It then builds that, and that will be the actual compiler that you use to build the rest of the system. So let's go back here. So in this case, I've actually selected CrossToolNG inside of the build root configuration, and then it will use the settings that I'd set previously to actually build a toolchain compatible with the Raspberry Pi. You also want to set the kernel configuration. So in the case of the Raspberry Pi Foundation actually provides a kernel for you, or they have a kernel that's on GitHub that actually has all of the patches necessary to run on the hardware, and a default configuration that's fairly decent. So I manually specified where that's located, and build root will actually download that kernel from Git and then build it. And of course, you select the kernel format image. So in this case, I'm using a Z image. There's also a proprietary bootloader recipe that will make sure to download both the bootloader and the GPU firmware. But those recipes are also specified. There are additional packages that have been added to this. So once you have the kernel, the toolchain, you need to have the contents of you need to pick what you want as the contents of the sysroot and the image. So all of these other options are basically what software and tools do you actually want on the system. Since our intention is actually building Qt, we need to pick dependencies of the parts of Qt we're actually interested in. One of the things that we have here, or one of the examples of the things we have here is if I want this to be a multimedia device, I need to have GStreamer, and for every video type or audio type that I want to support, I need the plugin. So I've actually selected those here as well. As part of this recipe, this build root recipe, this project, it actually has pre-configured 5.2 packages for Qt, and I've gone ahead and installed those, or built those, but I'll also show you how to build Qt yourself, or to configure Qt yourself, and how that works shortly. So after I've picked all of the things that I want for this image and configured it for the Raspberry Pi, all you need to do is save that xconfig and just run make. No arguments or nothing. What it actually does is it makes sure that it pulls down the toolchain, builds the toolchain, and then at the end, what you end up with is the actual tools you need. So If you look in the output folder, which is where it actually builds the thing, you'll see the host folder, and the host folder contains all of the host tools that run on your machine. So this is your compiler, and QMake and CMake, and all of the tools you need to build stuff. It also has the staging folder, and the staging folder is your sysroot. This contains all of the development headers. So if you go into user include, you'll see there's all the header files that you need to link against, or that you'll use to link against. And the same thing would be in lib here. So that's how Buildroot can easily provide you with the tools you need to even get to the point where you can develop for a given piece of hardware. So let's go back to the device. That. Okay. So when you get to the point where you want to build Qt for yourself, maybe you don't have a recipe available for your hardware, or there's some specialized thing. There's the trick you actually need to recognize. So in Qt 5, we changed the way that cross compilation works to make it a little bit easier. But here are the arguments inside of configure that are the most important ones. When you're actually configuring Qt, that is. So when you run configure, you use the -platform option to specify the make spec of the platform you're actually building from. And you get the make spec names from, let's go to the source folder here. Let's see, okay, so inside switch to code. So a make spec will be inside the make specs folders. And these actually represent the potential targets for your device. So if I'm actually building from a 64-bit x86 Linux machine, I'm going to select my platform make spec as Linux-G++-64. When you want to cross-compile for a platform, you need to pick a make spec that actually represents the platform you're building for. So if you were to build for a generic ARM device, you would pick something like, let's see, I know there's one of them on here that's ARM one. Yes, Linux-ARM.new EABI G++. That's an option for just a generic Linux build. But then there's the new option that comes in Qt 5, which is the device option. And this adds a little bit, or makes it a little bit easier to actually do the compilation for these common devices that we see. So if you go into the make specs folder and the device folder, you'll see some devices that you may actually be familiar with. You see the Linux-Keyboard G++ and the IMX53. And inside of these things are actually an additional configuration that makes building for these devices as simple as saying -device, Raspberry Pi, or just Pi. So we look at the actual Raspberry. Well, we can look at this. If you actually look inside of the make spec folder that for the Raspberry Pi, you'll see a couple of files. One of the files you'll see is the actual qmake.conf. And this is the file that actually specifies what's special about building for this device. When you run qmake, what does it need to append to the tools to actually cross-compile? So one of the special things about the Raspberry Pi is that the video drivers are installed to a non-standard location and have a non-standard name in some cases. So you'll see here that it actually appends an additional RPath link location into the sysroot and to where the location where the new video files are. And it'll do this anytime it tries to link something. The same goes for these additional include locations required by the EGL libraries, as well as actually saying what needs to be linked when you are linking against EGL. So this is also where you want to apply any additional optimization or C flags as well, so qmake_C flag. So just any customizations that you actually need to make for cross-compiling to the device. If you're creating a custom make spec, this is where you'll do it. Any additional arguments to configure. The other thing that's special about the Raspberry Pi is if you're doing embedded Linux, you'll actually need potentially an EGLFS hook. EGLFS stands for EGL full screen plugin, and that's what we use to display to the full monitor with an EGL surface that we can render OpenGL to. So in some cases with embedded hardware, you need to do special steps to initialize the hardware. So in this case, we actually, just have to call, say, PCR and host init. So just many of these functions are just things that are called to make it easier to actually, so it'll work really. In some cases, it's optimizations. And as far as configuration option goes, this is what it looks like when you're actually doing it. So dash prefix is the location that you want to install the libraries to. These are things that you want to install on the device. So in this case, the Qt libraries would be installed to /userlib. And the binaries that are intended to be run on the device will go to userbin. Host prefix is the location that you want the host tools that are compiled natively, like QMake, to be installed. In this case, the host here would be my build root host folder. So release build device Pi. That means that I want you to use that special Pi makespec, or Raspberry Pi makespec. And that'll have an additional cross-compile option that's part of the qmake.conf, where you can specify the location of your compiler with the prefix name in front of it. I do believe it's ARM-Raspberry Pi-Linux-GNU-EAVI, and then it would append GCC, G++, whatever it needs at the time. And then the sysroot variable is the other most important one, as this specifies where it needs to look for the include files of its third-party dependencies. And that's going to be your sysroot, or the staging directory and build root terms. Okay, so again, with Qt, after you run configure, make install, it installs into the sysroot. And then anytime you want to build Qt apps from that, or from the command line, you run qmake on that. It automatically appends any configurations you need to cross-compile. And then when you run make from there, it's already using your cross-compiler. And then that's code that you can copy to your device and run. All right, so I'll show you how to, if that's how you build from the command line. Now that you actually have Creator set up, or now that you have Qt set up, you can actually hook that into Creator so that you can build, run, and then run the code directly from your host machine Creator to the device, and then potentially debug, profile, whatever else. So if you actually want to set this up, you'll open up Creator and go to Options, and you want to go to the Build and Run section. And the first thing you'll do is you'll set up the compilers. So what you do here is that you hit the Add button. I'm not going to hit it now because I've already added this one. You set a name for this special cross-compiler you have, and then you locate the actual path of the compiler. So this is going to be in that host directory that was in your build root folder. So it's going to be host user bin, and then that ARM, well in this case ARM build root Linux GNU-AVI G++. That's your compiler. And then once you've specified just G++ or GCC, it knows where all the rest of the tools are. Once you've selected a compiler you want to build with, then you need to add a Qt version that you built. So you do this by specifying the location of QMake of the version of Qt you built. So in our case, that also is going to be in the host user bin folder that isn't as part of your build root. When you call make install when you built Qt, this is where that got installed. And so that's all I've specified there is that. And then from there, it's just a matter of creating a new kit. And in creator terms, kits are targets. So I've specified the name for Raspberry Pi. I set up a device, which is just, where's that guy at? It's just, in this case, I'm using an IP address to communicate over the network to the Pi. And then I also have the location of the sysroot, which it's also the staging folder in the build root output directory. And then I specify my Raspberry Pi toolchain, the Raspberry Pi GCC, and then I have an ARM debugger I had built previously, and so I have the location of that, and then the Qt version. So after you actually specify all that, it should just be a matter of creating a new Qt project, a Qt-based project, maybe building your project, and then that's it. So what I have here is actually just a simple Qt application. It's a quick application. What it does is it prints out some text and just scrolls it across the screen. So I have this on this machine. I'm just going to use that kit. In this case, I've just added the Raspberry Pi kit to this menu. You just say Add Kit in the Projects tab. Select your Raspberry Pi kit. And it should, if we're lucky, just push to this device if the stars are aligned. Hopefully it's able to do it. So it's compiled it, and I hope it can connect to the device. Oh wait, it won't, but I can make it. I have to connect to this special Wi-Fi network. Since there's no, I have to have Ethernet support to push things to the Pi. Let's see, Bing, Raspberry Pi. Let's just reboot it real quick for safety, just to make sure. But so that's the basics of it is that once you've specified the actual location of the device, it SCPs all of the, it knows what you would normally want to copy over to the device through these target deployments. So anything that would have been moved during make install, Creator automatically sees as something that needs to be copied over to the device. And so what it's going to do is, since that target device is specified by that kit, it's going to copy the data onto the Raspberry Pi and then run that over the network. So let's make sure. Actually got that right here. 101, yeah. Yes, yes, it does work. Awesome. Okay, so I'll just change that one line in the configuration real quick, and you can see that as well. So I'll go to Devices, Raspberry Pi, change it from hostname to 192.168.1.1. Live, okay, hit play, and hope for the best. There you have it. All right, so I don't really have time for the tips and tricks, but what I'm going to do is I actually go directly to the questions. Do you have any questions about what I've showed you here today? Any questions?
Actually, mic that.
Maybe it works. Huh? Yeah, all right. You want to talk about tips and tricks? We'll do some tips and tricks then. So again, generally when you're doing embedded work, you're going to use the EGLFS platform plugin. This is something that's newer in Qt 5, and again, it's just a single full screen surface. So that means that for your embedded device, when you're using Qt 5, you only have the option of displaying the contents of one application at a time. Something to keep in mind. Some of the EGLS environment variables that are quite useful, if you have this limitation, are the following. If you want to hide or unhide the cursor, you can use the EGLFS hide cursor thing, and that's just a Boolean 1 or 0. You can also set the swap interval, and this is a direct connection, or it's a direct relationship to EGL swap interval. In some cases, you'll also have to set the physical height and width of the device. This is used to calculate the DPI value for the scalable fonts and a few other things in Qt, as well as the actual. And in that case, you would specify that in inches or millimeters. I can't remember which one it is, but it is documented. And then there's the EGLFS width, height, and depth, which is the actual resolution of your screen. So, you know, in many cases, 800, 600 by 2418, what have you. And then finally, you have the EGLFS cursor. And this actually has to do with the mouse cursor itself. It's a location of a JSON file that specifies like what pix map to use for what cursor. So if you don't want it to be just an arrow cursor, you want it to be a skull or something weird like that, then that's where you'd specify that. If you do want to run multiple, if you need to display multiple applications content at once, you have the option of using the Qt Wayland module. And this actually allows you to write your own window compositor, and you'll be able to display the contents of multiple application windows at the same time. And one more thing, when you're doing embedded Linux development, there's a few modules that you might want to avoid if you're writing new code. Some of these are the QQuick 1 module. That's actually been deprecated as of 5.2. And then the QScript module. If you don't need it, don't use it. But in some cases, you still have to use it if you're doing non-QML code that needs to be scriptable. Qt widgets, if you're writing new code and you have access to OpenGL, don't use widgets, because with widgets you can't really take advantage of the OpenGL support. And then the Qt OpenGL module, which will be deprecated as of Qt 5.3. This is all the things that you really needed in the OpenGL module are already replaced in Qt GUI, with the exception of QGL widget, and that will be replaced with Qt OpenGL widget, which follows the naming convention of all the other GL classes. And yeah, that is actually it this time. So if anyone came up with any questions in that last 5 minutes.
Okay, any questions? Okay, so thank you again.
Yeah.